We discuss here the coordinates and the change of basis for a linear space. So we know that every linear space has a basis except linear space 0. Actually, we know that every linear space has infinitely many bases. So that means that when I choose one basis, every vector belonging to my linear space is a linear combination of the basis vectors, by definition. The coefficients of linear combination, they are called coordinates. So each time I change a basis, most of the time the coordinates of a vector will change. And we need to see what is the link between the coordinates of a vector in one basis relative to another basis. So how we go actually from one basis to another. For a given vector, its coordinates will be different from one basis to another most of the time. So that's where we introduce the concept of change of basis and transition matrix. So we are going to see what it is and how we can compute it, and you will see it's pretty easy actually. First, a reminder. We have a linear space V and we have a basis for V, set S with n vectors. So this linear space is n-dimensional, which means that every vector in that linear space is a linear combination of basis vectors by definition. The coefficients of linear combination C1, C2, C3, Cn, those coefficients are also called coordinates of the vector V relative to a basis S. So that's what the coordinates are. Those are just coefficients in front of the basis vectors when we write our vector V as a linear combination of basis vectors. We will also implicitly say that this basis is ordered in the sense that the order in which the vectors are given doesn't change. So V1 is the first vector in the basis, V2 is the second vector, V3 is the third, and Vn is the last, okay? Because obviously these coefficients follow the basis vectors. So when we write an ordered list here, these coordinates, they have the meaning. The first one multiplies the first basis vector. The second one multiplies the second basis vector. The third one will multiply the third basis vector. And the Cn will multiply the last basis vector, Vn. So that's what we mean by ordered basis. And our bases will be ordered, so we are not going to mention this again and again. It's assumed that bases are ordered. You don't swap the order of vectors. You just keep them as they are. So coordinates are just these coefficients in linear combination. Good news, for a given vector and a given basis, these coefficients are unique. So vector V will have only one set of coefficients, C1, C2, C3, Cn, that are his coordinates in basis S here. Okay, so that's just natural result, nothing special. Now we consider an example. The easiest one is R2. So we have linear space R2 and the standard basis E1, E2, which are just vectors 1, 0, 0, 1. That's a standard basis for R2. Obviously, standard basis for R3 will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Those are the standard basis vectors. So we know by definition that each vector in R2 is a linear combination of basis vectors. So it's a linear combination of E1 and E2. So if I have a vector U with components A and B, so entries A and B, this is what it means. A and B are coefficients in a linear combination. Those coefficients come in front of basis vectors. Okay? So this is our standard basis. So those coefficients are just the coordinates and the coefficients in linear combination. So that's what the coordinates are. Coordinates are just the coefficients of a given vector relative to a given basis. So these numbers in front. So for our vector u, its coordinates in standard basis S are A and B, right? And I keep writing here S. So you know these are the coordinates notation for coordinates in basis S. Okay, basis S. Obviously, for the standard basis of Rn, the coordinates of a vector in Rn are actually the components of the vector. And that's the characteristic of the standard basis for Rn. We see an example with R2, obviously. So if I have a vector u in Rn with entries and components, its coordinates in standard basis are actually just its components. But I keep writing S here just for you to know that these are the coordinates of the vector. And we deal with ordered bases, which means that order of these vectors here is fixed. Once we write it, we don't change it because it has a meaning. A multiplies the first guy, first basis vector, and B multiplies the second basis vector. So we gotta be careful who's first, who's second. So once we set a basis, we don't change the order. That's why we call it ordered basis. Obviously, this will be the case all the time, so we are not going to repeat ordered, ordered, ordered. It's understood that the basis is ordered. So the order matters, and coefficient, first coefficient multiplies the first basis vector, and second multiplies the second. So these coordinates, the first guy in the set of coordinates multiplies the first basis vector, etc. So an example, easy examples. If I have vector 2, 5 in R2, obviously 2, 5 is written as 2 times E1 and plus 5 times E2. That means that the coordinates of this vector in standard basis are 2 and 5, okay? Written like this in the standard basis. If I have a vector in R3, so vector u with components 3, -1, and 4, and this is standard basis of R3, then the coordinates of the vector u in standard basis are just the components of the vector. So that's very simple, and that's always the case for the standard basis. Now we go the other way around. I give you a set of coordinates of a vector in R4 in standard basis, and you give me the vector. So that's going to be easy, obviously. Vector u, its coordinates in standard basis are these numbers here. We need to find vector u. Well, by the definition of coordinates, we have the u is 2 times first basis vector of the standard basis of R4, plus -1 times the second, plus 4 times the third, and -2 times the fourth. So that's what you have here. So u will be a linear combination of vectors in the standard basis by definition, and these numbers here, the coordinates, are just the coefficients in front of the basis vectors. So 2 times the first basis vector in the standard basis, plus -1 times the second basis vector in the standard basis, plus 4 times the third basis vector in the standard basis, plus 2, plus -2 times the fourth vector. So obviously vector u is equal to this. So you see the difference in notation. This is a vector itself. These are the coordinates of the vector u in standard basis. We know for the standard basis that these numbers are the same as the coefficients of the vector. Okay, so this is a point in R4, and this is just a list of coefficients in front of the basis vectors. For the standard basis, the coefficients, so the coordinates, are the same as the entries of the vector. But that's only for standard basis. Now we give ourselves another basis for R2. So basis created by these two vectors, 1, 1 and 1, 2. Well, these are two vectors from R2. Dimension of R2 is 2. These are two vectors that are linearly independent in R2, so they are bases. How do I know? Well, they are not scalar multiple of each other. Another way, you can quickly compute the determinant and see the determinant is 1, so it's different from 0. So these two vectors are linearly independent, And since R2, its dimension is 2, I need only 2 vectors from R2 that are linearly independent to have a basis. So that's what I have here. So by the definition of a basis, we know that any vector in R2 is a linear combination of basis vectors, right? Any vector in R2 is a collinear combination of basis vectors 1, 1, and 1, 2. But that's normal because R2 is span of B, span of these 2 vectors. So that's just the definition. So U is equal to some number A times vector 1, 1 plus some number B times vector 1, 2. So that means that the coordinates of a vector U in basis B are these numbers A and B. Okay, so those are the coordinates of vector U in a basis B. So let's say I'm given coordinates of some vector U in a basis B, and coordinates are 4, 2. Find the vector U. What's the vector whose coordinates are 4, 2 in basis B? Well, that's easy by the definition of the coordinates. U is linear combination of basis vectors, and the coefficients are 4 and 2. So 4 times the first basis vector plus 2 times the second basis vector. So I just do the algebra and I get that U is the vector 6, 8. By the way, we know already that coordinates of a vector in a standard basis, are equal to the coefficients that you have or entries in the vector. But you see very well that coordinates in a different basis are different numbers. These are just coordinates of vector 6, 8 in basis B. The coordinates are 4 and 2 because it's 4 times first basis vector from basis B plus 2 times second basis vector from basis B. Another example. I'm given again coordinates of some vector U in basis B, and coordinates are negative 1 and 5. So coordinates of B of U in basis B are negative 1 and 5. So coordinates in basis B. Find the vector U. Well, that's not complicated. Again, by the definition of coordinates, these are the coefficients in front of the basis vectors. So I have negative 1 times the first basis vector from basis B plus 5 times the second basis vector from basis B. So I compute and I get that the vector U is vector 4, 9. So that's how very easily, by using the definition of coordinates, we can find the vector once we are given its coordinates in a given basis. So that's straightforward. Just write the linear combination and you're done. Now the more complicated part will be given a vector U, find its coordinates in a different basis, in a basis B or basis C, so that's another story that we need to see. Another example, so the same basis B, 1, 1, 1, 2, so that's a basis for R2. Now we are given a vector U in R2, so vector 2 minus 2. And our task is to find the coordinates of the vector U in the basis B. Okay? So we need to find the coordinates of U relative to the basis B. That means that we need to find numbers A and B such that A times first vector plus B times second vector is equal to our guy. So what are A and B such that A times the first basis vector plus B times the second is equal to the vector U. So we need to solve the non-homogeneous system. So if we write augmented matrix form, so we need to solve this using our Jordan. So we knew already how to do this because finding A and B is pretty much finding the coefficients of linear combination. So we know how to do that. So we apply Gauss Jordan and we get the solution AB. So A6, B is negative 4. So A and B form the coordinates of the vector U in basis B. So the coordinates of the vector U that is given at the beginning, 2, negative 2. So the coordinates of this vector relative to basis B are numbers 6 and minus 4. The meaning of this is the vector 2 minus 2, you get it when you multiply 6 times the first basis vector of basis B plus negative 4 times the second basis vector of the basis B. That's the meaning of this. So how do we find the coordinates of a given vector? So given vector, given a basis, how do we find coordinates? We need to solve non-homogeneous system by Gauss-Jordan. That's all. The solution is actually our coordinates. So that's what we get. Another example, we have a vector 2, 6 in R2, and we need to find coordinates of vector 2, 6 in the basis B. Again, we need to solve non-homogeneous system. So this comes from the definition of linear combination. We need to solve non-homogeneous system where the matrix A is actually in columns has the basis vectors from B. So this is the first basis vector, this is the second basis vector. So we just put them in columns and we solve the non-homogeneous system, augmented matrix, Gauss-Jordan, apply Gauss-Jordan. So in this case it's not that complicated. So we get the result, negative 2 and 4. So for our vector 2, 6, its coordinates in the basis B are numbers negative 2 and 4. So coordinates of vector u in basis B are numbers minus 2 and 4. So that's what it means. It means that this vector 2, 6 is linear combination of vectors 1, 1 and 1, 2, and the coefficients of linear combination are negative 2 and 4. So this vector is negative 2 times 1, 1 plus 4 times 1, 2. That's what when we do that, we will get our vector back. So these are the coordinates of u in basis B. That's what it means. So again, what we need to do when we need to find coordinates of a given vector is to solve non-homogeneous system. Our vector is on the right side, unknowns will be our coordinates, and the matrix is formed by the basis vector. So each basis vector is put in a column. So that's the strategy. And this is good in R2, R3, R75 is the same procedure. Now it's time to complicate things and have something more interesting. Because by now we know how to compute coordinates of a given vector in a given basis. That's easy, just solve a non-homogeneous system and that's it. But what if I give you, let's say here, 3 bases for R3. So I have a standard basis, and I have basis B and a basis C. So then I could ask you, oh, find me coordinates of a given vector in basis B. Well, that's easy. Solve non-homogeneous system, that's super easy. Or give me the coordinates of the vector u in basis C. Well, again, it's easy, just solve the non-homogeneous system. Obviously, when the system is bigger, it takes more time. So in itself, this is an easy process. But now I can make this process a little bit longer and a little bit tiresome. What if I tell you, I give you 100 vectors from R2. So not only one, I give you 100 of them, or 1000. And I ask you, find me coordinates of those vectors in basis B. Or find me the coordinates of those 100 vectors in basis C. Well, each time you're going to solve the system, fine. But that's very long. There's a lot of systems to solve. So if you're half smart, you would just take your matrix, because it's always the same, and put the 100 vectors on the other side, and then solve it all at once. So that would be one approach. But still, there's a lot of work involved in all this. It's going to be long, long, long. So just looking for coordinates of one vector is easy, it's one system to solve. But if I give you 1000 vectors, and I ask you for coordinates of all of them in basis B or in basis C, well, you need to solve something like this 1000 times. Or if you know a little bit better the theory, you know that your matrix is always going to be the same, and everything that changes is the vectors. So you just put them here, and you have like gigantic augmented matrix system, apply Gauss-Jordan to everything, and you solve. So
That would be still long. But I can complicate things even more. I can tell you, hey, I give you coordinates of a vector u in basis b. These are the coordinates. Find me coordinates of the vector u in basis c. I could do the other way around. I can give you coordinates of a vector in basis c and tell you, find me coordinates of the same vector in basis b. Well, that's a little bit more involved. So we go from very simple, easy, one vector at a time, and then we can say, hey, but if I give you a lot of vectors, you're going to suffer, even though each time you solve the system and you know how to do it, but it's very long and it's painful. And then I can make it even more puzzling, telling you, hey, I give you coordinates in one basis, give me the coordinates of the vector in another basis. Good luck. So these are the questions we can ask. So there is a good way to solve all this all at once. So a smart and efficient way to solve these problems, all of them at once, is to build what is called a transition matrix from one basis to another. What is that? We will see how to build it first. And it's not complicated. Again, you will need to solve using Gauss-Jordan, but the system will be smaller and you solve it once in your life. So the transition matrix will be something very important to solve our problems. So this is the notation. I have a transition matrix from basis S to basis B. So that's how I write it. Transition matrix T from basis S to basis B. Okay, from basis S to basis B. Transition matrix from basis S to basis C. Okay. Transition matrix from basis B to basis C. And we will see how to use them also. So computing them is not complicated, but we will see how to use them in a very efficient way. So all those problems will be solved extremely fast. So a couple of remarks. Every transition matrix that we have, and we will have a lot of them, they are all square, all of them, and they are all invertible, all of them. So transition matrix is a square matrix and it is invertible matrix. So it's beautiful. More importantly, transition matrix from basis B to basis S is the inverse of the transition matrix from basis S to basis B. So once I find one, the transition matrix from in the other direction is the inverse of the previous matrix. So transition matrix from basis C to basis S is the inverse of the transition matrix from basis S to basis C. And also transition matrix from basis C to basis B is the inverse of the transition matrix from basis B to basis C. So you swap order, you need to compute the inverse. So we will see how to compute transition matrices and how to use them. So here is a smart way to do things. So again, we have our three bases. So illustration how to build the transition matrix from, let's say, basis B to basis C. So basis B is here and basis C is there. So what do I need to do to build the transition matrix from basis B to basis C? So basically I have people that are expressed in their coordinates in basis B, and I would like to know what their coordinates are in basis C. So first thing to do is to build the matrix. But what's the idea of building the matrix? How does it work? To find the coordinates, so we need to find the coordinates of the basis vectors from basis B. So we are starting from B to C. So we need to find the coordinates of the basis vectors from B in terms of the basis vectors from basis C. Because I need to go from basis B to basis C. So what I'm doing is expressing everybody in basis B as a linear combination of people in basis C. So I go from B to C, so people from B need to be expressed in terms of vectors in C. So people from basis B need to be expressed as linear combinations of vectors in basis C. So what does it mean? Well, it means that I need to find constants A, B, C, D such that A times first vector from basis C plus B times the second vector from basis C is equal to the first vector from basis B. So I need to solve the non-homogeneous system. Also, so this is expressing the first vector from basis B as linear combination of vectors in basis C. So I'm going from B to C. So people from B need to be linear combination of people from C. And then the second basis vector from B need to be expressed as linear combination of vectors in basis C. So I need to solve this non-homogeneous system. So once I'm done, I put the solutions in vectors, so in columns of a matrix, and that's my transition matrix from basis B to basis C. So the first column contains the constants in front of the basis vectors from C relative to the first basis vector is in B, and people in the second column are coefficients in front of the vectors from basis C relative to the second vector in the basis B. So first column for the first vector, second column for the second. So the idea is express each person from basis B as linear combination of people in basis C. Okay, so I need to solve these two systems. Obviously, the matrix is the same. You check the matrix is the same because it's just these two vectors, obviously. So I need to be a little bit smart because I need to solve two systems with the same matrix. So being smart a little bit helps. So I need to put my matrix. So these are vectors from C slash, and here you find vectors from B. This is what you have. So I'm going to express people from basis B in terms of vectors in basis C. So C slash B. In the book they say old basis, new basis, and then you have new basis slash old basis. So that's what you have. Expressing people from B in terms of people in C. So I apply Gauss-Jordan. Hopefully I didn't make any errors. And at the end I'll have identity here. So this is the form identity slash transition matrix from B to C. And that's what is going to happen when you have these square systems. You will have identity on one side always, and on the other side you'll have transition matrix. So once I solve, so this is my transition matrix. So just copy the matrix. So the transition matrix from basis B to basis C is this matrix here. Okay. We know also, so we see it's square and it is invertible, obviously. So we know also that transition matrix from basis C to basis B will be the inverse of this guy here. We saw that. So once you find one, you can compute the other by computing the inverse. If computation of inverse is fast. Obviously here we have 2 by 2 matrices, that's fast, but even you have 7 by 7, it's not that fast, so you better solve the system again. So I computed the inverse, and inverse is here. So this is the transition matrix from basis C to basis B. So it's the inverse of transition matrix from basis B to basis C. So that's what I get. So how do I use this now? I know how to find the transition matrix. How do I use it? So given coordinates of U in basis B, let's say 2 and -4, for instance, find the coordinates of U in basis C. So that's not complicated. I have coordinates in basis B, and I need to find coordinates in basis C. For that, I'm going to use the transition matrix that brings people from B to C. So all I need to do is do the product transition matrix from B to C times the coordinates of the vector in basis B. And I will get, as a result, the coordinates of vector in basis C. So you see, this transition matrix brings people with coordinates in B into coordinates C. So I provide you the vector with coordinates B, you multiply, what you will get at the end is the coordinates of the vector in basis C. So in our case, I'll just compute, do the product. So this was from B to C, and this is 2 minus 4 in B. So I do the product, have negative 1, and then I have negative 3 plus 4, that's 1. So these are the coordinates of the same guy in basis C. I still don't know who's the guy. I know his coordinates in basis B, and I know his coordinates in basis C. But it's not complicated to find who's U. U is, it says here, negative 1 times the first vector from basis C, which is 1, 4, plus 1 times the second vector from basis C. That's what it is. So U is negative 1, that's negative 2, negative 4, and negative 2 is negative 6. So that's my guy. The vector U was negative 2, 6. Oh, you can get it from here also. It's 2 times 1, 1, plus minus 4 times 1, 2. Okay, so that's fine. If you compute, you'll get the same result, obviously. Okay, so that's the idea. Given coordinates in one basis, find the coordinates of the same vector in another basis. Still, you don't know who's the vector, but doesn't matter. So it's easy to find using the transition matrix. Here, I was given coordinates in basis B. I had to find the coordinates of the vector U in basis C. What do? I use the transition matrix that brings people from basis B to basis C. So this is the transition matrix. I just multiply the transition matrix for people from B to C times the coordinates of a person in B, compute, and get the coordinates in basis C. Simple, simple, simple. So if I give you 1000 vectors now, you just do the product matrix vector all the time. It's straightforward. When you want to know who's the vector actually, well, you have his coordinates in basis C. So this means minus 1 times first vector of basis C plus 1 times the second vector of basis C. Similarly, coordinates of the same guy in basis B, this means 2 times the first vector from basis B plus negative 4 times the second vector of basis B. And obviously you're going to get the same result because it's the same vector U. Its coordinates in 2 different bases, basis B and C, are different. That's normal, that's fine. So in order to compute the transition matrix from basis B to basis C, we had to solve this augmented system. So we put the basis C on this side slash all the basis B on the other side. Obviously, if we had to find the transition matrix from basis C to basis B, we will swap these two. But we already have it, so we don't need to do the job. We can have the other transition matrices also. So we built already matrix from B to C, and then since it was 2 by 2, it was easy to compute the inverse, or if you wish, again, solve the system by Gauss-Jordan and get the transition matrix from C to B. Let's now find the transition matrix from the basis B to the standard basis S. What does it mean? Again, we are looking to express every vector from basis B as linear combination of vectors in basis S. So, vector from basis B needs to be a linear combination of vectors in basis S. So I need A times first standard vector plus B times second standard vector equal to the first vector from basis B. So that's done, and then I need also to find the second vector from B as linear combination of vectors from basis S, from the standard basis. So basically I need to solve this augmented system. The matrix is 1, 0 in both cases, 1, 0, 0, 1, and slash, and then I have 1, 1, first column, second column, 1, 2. So I need to solve this. So I need to end up with the form identity something. Well, good news, I'm already there. The system is already in that form, identity slash something. The something is a transition matrix from basis B to basis S. So I already have that form, so there's nothing to do. This one was free. So the transition matrix from basis B to basis S is actually here. Matrix 1, 1, 1, 2. It was actually just the matrix that I formed by the vectors from basis B. So when you go from some basis to the standard basis, well, it's obvious, it's very quick, because there's nothing to do actually, because you will have a system identity slash something. That something is your transition matrix. Okay, so that was easy. How about finding transition matrix from standard basis to basis B? So I have people in standard basis, and I want their coordinates in basis B. So procedure is the same. I take every vector from basis S, standard basis, and I express it as linear combination of vectors in basis B. Okay, so I need to solve the system like this. Straightforward. So apply Gauss-Jordan. Once you're done, you get the form identity slash something. That something is the transition matrix from basis S to basis B. So very simple. So for us, I'm doing all these steps now. Soon, I will just form the augmented system, apply Gauss-Jordan, and get it. So there's no point of repeating this 62 times. Obviously, when I only have two vectors, it's not a big burden, but if I have a linear space that has 5 or 6 basis vectors, then repeating this 6 times is not really good use of time. I can immediately form the matrix system to solve. Similarly, if I need to find the transition matrix from basis C to basis S, so from C to the standard, we know the procedure. We need to solve this system. So I express every vector in C as linear combination of vectors in S. So I get this system here. So you see what's going on. S comes here, slash C goes on the other side. So they're kind of swapping. Again, standard basis gives me identity matrix already. So immediately I have the form identity slash something. So this something is automatically the transition matrix. So here again, no work required. Transition matrix from basis C to standard basis is here, the basis vectors in basis C. Straightforward. Now if I need to find the transition matrix from standard basis to basis C, that means I need to express every vector from basis S as linear combination of vectors in basis C. So people from basis C will form a matrix, slash, and then I'll put people from basis S on the other side. Right? Straightforward. Now I use Gauss-Jordan again to solve. And once I solve it, I get the form identity slash something. That something is automatically the transition matrix from standard basis to basis C. So those things are done very easily. The procedure is always the same. You have one going from one basis to another, and then you need to solve the system, another basis slash the original basis. So that's the same procedure all the time. Now we are going to see how to use this efficiently to find coordinates of one vector given in one basis and then find its coordinates in another basis. Another application, if we are given coordinates of a vector, so vector u, we are given coordinates of that vector in basis C, we need to find its coordinates in basis B and basis S, the standard basis. So vector u, I don't know who's the vector u yet. I know his coordinates in basis C. Coordinates are -2 and -5. I need to find first coordinates of u in basis B. Oh, that's what I need to find. Well, that's easy to find because all I need to do is, since I already have transition matrix from basis C to basis B, I need to multiply that matrix by the coordinates of the vector in basis C. Result will be the coordinates of the vector in basis B, because this guy brings people from with coordinates in C into coordinates B. So I just need to multiply this matrix by the coordinates in C. So the transition matrix from basis C to B is here, and I multiply it by the coordinates of the vector in basis C, do the computation. The result is the coordinates of the vector u in basis B. Remember, transition matrix brings people, this one here, from coordinates in C into coordinates B. So coordinates C into coordinates B. Provide me coordinates C, multiplication will give you coordinates B. If I want to find the standard coordinates of the vector u, well, it's simply transition matrix from basis C into basis S times the coordinates of the vector in basis C. Transition matrix times the vector, do the product, and I get the coordinates of the vector in basis S, which is the standard basis, coordinates 3, 2. Now we know that the coordinates in standard basis are actually just the components of the vector. So that's something that is known. So the vector u is actually vector 3, 2. We know that the vector itself and the coordinates of the vector in standard basis is pretty much the same thing. Coordinates are just the entries of the vector. So standard basis is linked with the vector, right? The entries of the vector are actually the coordinates of the vector in standard basis. So that's straightforward. So that's one application. Another one, I'm given a vector u, so this is a vector, 6 minus 3, and I need to find the coordinates of the vector in standard basis, in basis B and basis C. Well, the good news is I already know that the coordinates of the vector in standard basis are actually the entries of the vector. So that's straightforward, there's nothing to do there. Okay, so coordinates of vector u in standard basis are just the entries of the vector. Now, the coordinates of the vector in basis B, well, that's something that requires work. So I need transition matrix from standard basis to basis B. Okay, here it is, and I multiply it by the coordinates in standard basis, so by the vector itself actually. Do the product, and here I get the coordinates of the vector u in basis B, 15 and minus 9. Okay, so that means that this vector u is 15 times first basis vector in basis B, plus minus 9 times the second basis vector in basis B. That's the meaning of the coordinates. Now if I need to find the coordinates of the vector u in basis C, no problem. I just need to multiply the transition matrix from standard basis to basis C by the coordinates of the vector in standard basis. So just do the product and we get this. So these are the coordinates of vector u in basis C. So you see you have your vector, its coordinates in standard basis, those are the components of the vector, that's normal. But now in any other basis you will have different coordinates. So that's also normal, that's fine. So these coordinates in basis C and these coordinates in basis B represent the same vector u. So same guy, two different sets of coordinates relative to different bases. So that's normal thing. We can do similar things in R3. So here is an example how to build transition matrices, let's say between three different bases of R3. So I have standard basis of R3, I have basis B, which is another basis in R3, and basis C. So all of them, since they are bases, they span R3 obviously. A quick verification, obviously this will create an identity matrix, so determinant is 1, so matrix is invertible, so that means all three vectors are linearly independent. If you compute determinant for this matrix here, if you form a matrix 3 by 3, you find that determinant is different from 0, it's actually -2. So the matrix is invertible, so the reduced echelon form is identity, so all three vectors are linearly independent. Similarly, for basis C, you can form a matrix and compute a determinant if you wish. Determinant is -2 in this case also, and that means that reduced echelon form is identity, which means matrix is invertible also, so all three vectors are linearly independent. In general, when we are given bases, we trust that the vectors are linearly independent, so we don't need to make the verification. So we just assume, given three bases, so we assume that these are the bases S, B, and C. Indeed, the vectors are linearly independent, so we don't need to verify, but I'm just specifying here. So R3 is span of standard basis, span of basis B, span of basis C, obviously. So let's now compute the transition matrix from basis B to basis S. S is standard basis. We already know what's going to happen. So just schematically, what we need to solve is an augmented system of the form S/B. So transition matrix from B to S means that I need to express every vector in B as linear combination of vectors in S. Okay, so S will form a matrix slash and B will form the right-hand side member. So that's what I need to solve. And I need to end up with the form identity something. Well, good news, I already have that form because S is standard basis, so I have identity on the left side immediately. So whatever is on the right side is a transition matrix. So I already have the correct form, identity slash something. The something is the transition matrix we are looking for. So the transition matrix from basis B to standard basis is basically just a matrix formed by the column vectors of basis B. Straightforward. Similarly, if I need to find transition matrix from basis C to standard basis, again I'll do the same process. I'll have identity, and then on the other side I'll get the three vectors from basis C. So I have the correct form identity something. So again, finding a transition matrix in that case is straightforward. So whenever you have transition matrix from some weird basis into standard basis, well, the transition matrix is just the column vectors of the weird basis. So here, those are column vectors of B, here are the column vectors of basis C. So that's the easy part. But what happens if I need to find the transition matrix from basis S, so the standard basis, to basis B? So I need to express every vector in S as linear combination of vectors in B. So people from S will be on the right side, and people from B will form the matrix. So I need to solve schematically B slash S. So I take the three vectors in correct order, obviously, from basis B slash the three vectors in correct order of the basis S, the standard basis. Then I go by Gauss-Jordan, and 2 days later I compute, and I get on the left side identity, and on the right side, whatever it is, will be the transition matrix. So I have the form identity slash transition matrix. So transition matrix from basis S, standard basis, to basis B is given here. I just copy paste the matrix. By the way, in this specific case, you remember that this is the way we compute the inverse of the matrix on the left. That's the same procedure, because on the right side is the standard basis. So basically, it is reminding us of something we already know. However, we still need to do the process. There is no escaping that. You need to go through Gauss-Jordan. And obviously, since these three vectors are linearly independent, so this matrix 3 by 3 is invertible, so we'll get identity on the left side. Always, always, always. So when you have form identity slash something, the something is the transition matrix. Okay, so let's find now the transition matrix from basis S to basis C. So again, I need to express every vector in S as linear combination of vectors in C. So people from S will be on the right side of the equation, and people from C will form the matrix. So I need to schematically solve C slash S. So I put the basis C here, the vectors in columns, slash the vectors from basis S in correct order. Again, Gauss-Jordan, and 2 days later I get identity slash something. This something is the transition matrix from the basis S to basis C. Again, this reminds us of computation of the inverse of this matrix here. So now we have those transition matrices. Let's now compute the transition matrix from basis B to basis C. So here, what does it mean? Well, it means I need to express every vector from basis B as linear combination of vectors in basis C. That means that people from B will be on the radial side of the equation, and people from C will form the matrix. So I'll technically solve something that has this form, C slash B. So I put the people from basis C slash people from basis B, and then use Gauss-Jordan to solve an elementary row operations, obviously. So after 2 days of computation, I'll get identity on the left side slash something on the other side. This something is the transition matrix. So this is the transition matrix from basis B to basis C. So we got it by expressing each vector from basis B as linear combination of vectors in basis C. So that was the procedure. So Gauss-Jordan each time. And we know we are going to get identity on this side because the three vectors here are linearly independent. So the reduced echelon form will be identity on the left side. And to the right side, well, we will get our transition matrix there. Now, to get the transition matrix from C to B, we could compute the inverse of this. Well, it's not so obvious because we have fractions, it's ugly, so we are going to simply do the process all over again. So to find the transition matrix from basis C to basis B, I need to express every person in basis C as linear combination of people from basis B. So basically I need to solve something like B slash C. So people from B are in the matrix and people from C are on the right side. Again, I use Gauss-Jordan in elementary operations. After computation, I know I'm going to get identity on the left side because these three vectors are linearly independent, so the reduced echelon form will be identity, that's obvious. Because I have three vectors here with three components. So I have identity slash something. This something is a transition matrix from basis C to basis B. We could verify that this is indeed the inverse of the previous transition matrix just by multiplying them. The result needs to be identity, obviously. So that's how we proceed. What we need now is just 1 or 2 examples of application, how to find coordinates of certain vectors when they're given in one specific basis. And we are going to use, just like previously, we are going to use the transition matrices. We can have another example. So given a vector in R2, so vector 2, 0, 1, for instance, Question is, you need to find the coordinates of that vector u in basis B. So we need to find coordinates of u in basis B and also coordinates of u in basis C. Obviously, coordinates of u in standard basis are 2, 0, 1. So that's super easy, we don't need to ask for that. So how do I find coordinates of u in basis B? Well, easy. I take the transition matrix from standard basis to basis B, and I multiply it by the coordinates of the vector in standard basis, which are just entries of the vector. So transition matrix from standard basis S to basis B, we already computed that, times the coordinates in standard basis, do the product, and we get the coordinates of the vector in the basis B. Similarly, if we need to find the coordinates of vector u in basis C, we need transition matrix from standard basis to basis C, so we already computed that, and we multiply that matrix by a vector containing coordinates of u in basis S, which is standard basis, so those are just the entries of the vector. So we have already computed this matrix, transition matrix from standard basis to basis C. We multiply it by the coordinates of the vector in standard basis. After computation, we get the coordinates 3, 0, negative 1. So these are the coordinates of vector u in basis C. What does it mean? It means 3 times first vector from basis C plus 0 times the second plus negative 1 times the third. If you do that, you'll get 2, 0, 1, obviously, at the end. That's what's supposed to happen. Another example. We are given coordinates of a vector u in basis C. So the coordinates are given as negative 1, 2, and 0 in basis C. What does it mean? It means that this vector u is negative 1 times first basis vector from C, plus 2 times the second basis vectors from C, plus 0 times the third basis vector from C. That's the meaning of this. So those are the coordinates of u in basis C, and we need to find the coordinates of u in standard basis. So we need to actually find what's the vector, and we need to find coordinates of u in basis B. We remember that the coordinates of u in standard basis are the same as the entries of the vector, by the way. So we can use the transition matrix from basis C to standard basis and multiply it by the coordinates of u in C, in basis C. So this is just the matrix containing vectors from basis C, and we multiply it by the coordinates in basis C. So basically, they're just distributing, it's minus 1 times this, plus 2 times this, plus 0 times this. Linear combination, basically, by definition. And we get the vector u, its coordinates in basis S are 3, 3, 5, but these coordinates are actually giving us the vector immediately. The vector is 3, 3, 5. So we know already that the entries of the vector are its coordinates in standard basis. So those two things are the same. Okay, so now let's compute the coordinates of u in basis B. How do we do that? Well, we need a transition matrix from basis C to basis B. We computed already that. And we multiply that matrix by coordinates of u in basis C. So this is the transition matrix from C to B, multiplied by coordinates in C. We do the computation and we get the coordinates of the vector u in basis B. What does it mean? Well, it means that these are the coefficients of linear combination. So it's 11 over 4 times first basis vector in basis B, plus negative 1 over 4 times the second basis vector of basis B, plus 1 over 2 times the third basis vector of basis B. So when you compute, obviously you will want to get the same vector. We know that. But I'm just doing it here to show you that you'll always get the same vector at the end. The coordinates are different, obviously. In basis B, it's different from the coordinates in basis C, which is different from the coordinates in standard basis. But it's the same vectors. It's the vector u that has different coordinates in different bases. So that's the standard procedure. How to find a vector once you have the coordinates is just a linear combination. And how to find coordinates of a vector in specific basis? Well, you need coordinates given in, let's say here, basis C, and you need transition matrix from C to B in order to find coordinates for vector in basis B. So that's pretty straightforward, and it's not complicated in itself. It just requires a little bit of computation for the transition matrix mainly. An important observation: the vector 0, 0, 0, so the vector 0 from R3, its coordinates in every basis of R3 are 0, 0, 0. Why? Because people in the basis are linearly independent. And by the definition of linear independence, well, the only numbers that you can put in front of the linear independent vectors to get vector 0 are 0, 0, 0. So obviously vector E1, E2, E3 are linearly independent, so 0 times this plus 0 times this plus 0 times this gives vector 0, 0, 0. For the coordinates of the vector 0 in basis B, obviously it's 0, 0, 0. Why? It's 0 times the first vector plus the 0 times the second plus the 0 times the third. And we know that this must be the case because the vectors in any basis are linearly independent. And if you remember the definition of linear independence, the vectors are linearly independent if and only if the only solution for A times this plus B times this plus C times this equal to vector 0 is 0, 0, 0. We know that. Similarly for basis C, the coordinates of vector 0 in basis C are 0, 0, 0. Again, the reason the vectors in the basis are linearly independent. And by the definition of linear independence, that means that the only solution of this homogeneous system is 0, 0, 0. So that's very simple. So vector 0, its coordinates in any basis are 0, 0, 0. In R2, it would be 0, 0. In R3, it's 0, 0, 0. In R4, it's 0, 0, 0, 0. And in R75, well, you have 75 zeros. Here we go with one interesting example. So I have B set of two vectors here. They are linearly independent, obviously, because they're not scalar multiple of each other. And then I have another set C with these two vectors that are also linearly independent, obviously, because they're not scalar multiple of each other. And those two sets of vectors, they are basis for a linear space called W. So what's W? W is just span of these two vectors, so span of basis B, which is the same as span of basis C, so span of these two vectors. So W is just a linear space generated by two vectors. These two or these two is the same space. By the way, you could verify indeed that indeed this vector is linear combination of these two, and this vector is linear combination of these two. Also, you could verify that this vector is linear combination of these two, and also that this vector is linear combination of these two. That's not complicated. If you want to make sure that they really generate the same space, this guy belongs to this space, this guy belongs to this space, and the other way around. Okay, so W is span of B, which is the same as span of C. Obviously, W contains people that are scalar multiple of this plus scalar multiple of this. So these are vectors with 4 components. So W is a linear subspace of R4. That's just an observation. So here we are given a vector U with 4 components, and then we can ask some questions. Does U belong to W? So that one is easy to see. How do we do that? Well, all we need to do is solve the system here. So the first question is, does U belong to W? The second question is, what are the coordinates of u in basis B and what are the coordinates of u in basis C? Well, obviously that depends, and we need to solve some of these equations. So first thing to solve, to see if u belongs to the linear space W, is to solve this equation. Is u a linear combination of basis vectors? So we solve it using Gauss-Jordan, and indeed we have a solution for 3. Therefore, u is in the linear space W, so u belongs there. To find the coordinates of u in basis B, well, these are two vectors from basis B. That's easy also, because we need to solve the same system practically that we just solved, and the coordinates will be 4 and 3. So now we need to see what are the coordinates of u in basis C. We can also find coordinates of the vector u in basis C. How do we do that? Well, it's simple. We just need to find u as linear combination of vectors in basis C. So basically we need to solve this non-homogeneous system. So d1 times the first vector from basis C plus d2 times the second vector from basis C equal to our guy. So basically we are solving augmented matrix system by Gauss-Jordan. So once we finish solving, we get something like this. The solution d1 and d2 are 4 and negative 1 over 2. So at the same time, we know that our vector is the linear combination of basis vectors in basis C, obviously, and the coordinates of our vector in basis C are 4 and negative 1 over 2. So that's simple. It's just normal solution process for non-homogeneous system. How to find coordinates of a vector in a given basis? Well, you need to solve non-homogeneous system. Very simple, standard procedure. Couple of interesting remarks. Our space, linear space W, is span of basis B and span of basis C. Both of them have only 2 vectors inside, obviously. So the dimension of W is 2. We have 2 linearly independent vectors in the basis. Another important thing to notice, obviously W is linear space, so it contains vectors 0 from R4. We remember that W is subspace of R4. So some vectors from R4 actually live in W. Among them is vector 0. So 0 with 4 components, 0, 0, 0, 0. Okay, 0 from R4. So in basis B, the vector 0 from R4, its coordinates are 0, 0. Why? Well, because it's 0 times the first vector of basis B plus 0 times the second. That's equal to 0. Obviously, vector 0, so it's linear combination of them, and the only coefficients are 0 and 0 because these 2 vectors here are linearly independent. So this is actually the definition of linear independence, obviously. What I want to make sure you understand, we have vector 0 from R4. That guy has 4 components. Now, the coordinates of this guy in basis B has 2 people inside, the coordinates are 0 and 0. Okay? So you see that coordinates, there are only 2 because we have 2-dimensional linear space W. Okay? So we have 2 basis vectors. So we have 2 coefficients. Okay? So this is the coordinates of vector 0 from R4 in basis B. Similarly, the coordinates of vector 0 from R4 in basis C are also 0, 0 because these 2 basis vectors are linearly independent, and this is the definition of linear independence actually. So the only 2 coefficients that will satisfy this equation are 0 and 0. That's why the coordinates are 0, 0. Coordinates are just coefficients in front of basis vectors. So we have 2 basis vectors, 2 coefficients. Okay? So coordinates are coefficients in front of basis vectors. Fine. We can also find the transition matrix from basis B to basis C, for instance. Now, what does it mean? Well, it means that I need to express every vector in basis B as linear combination of vectors in basis C. So, first vector in basis B needs to be expressed as linear combination of vectors in basis C. Second vector in basis B needs to be expressed as linear combination of vectors in basis C. So we simply need to solve the system. So this is C slash B, and we solve it. What is important to notice, we have two linearly independent columns, which means we will have two linearly independent rows, which means we will have these rows of zeros below. That's totally normal. That's what is supposed to happen. And what will happen also, you see in the corner, you have identity 2 by 2. Okay, so the solution of this system is simply for A and B, A is 1 and B is negative 1 over 2. C and D, C is 0 and D is 1 over 2. So we just put them in our transition matrix. So you see how easy it is. You form your system, solve using Gauss-Jordan. At some point you'll get your reduced echelon form, obviously. But what you notice here is identity 2 by 2 and bunch of zeros below. Perfect, because this is reduced echelon form. And on the other side, the corresponding 2 by 2 will be your transition matrix. Obviously, it's going to be 2 by 2 because each basis has two vectors. So you have A and B for this guy, A and B, and you have C and D for this guy, C and D. Okay, we know the transition matrix is always square. In this case, it is 2 by 2 because our linear space is of dimension 2. It has two vectors in bases. So it is square 2 by 2, and obviously it is invertible, always. So that means that I can very quickly, because this is 2 by 2, I don't need to resolve again. I can just compute the inverse of 2 by 2 because I remember the formula. So to get the transition matrix from basis C to basis B, well, we could redo all the process, express every vector from C as linear combination of vectors in B. Fine, but I'm smart. I learned a couple of things. So I know that transition matrix from basis C to basis B is just the inverse of the transition matrix from basis B to basis C. So it's the inverse of this guy here. And this is 2 by 2. Okay, it's easy to compute the inverse of 2 by 2. So I take advantage of that, and this is what I get as transition matrix from basis C to basis B. If you don't remember this, it's fine, you just redo the process. What I want to make sure you understand is that we have linear space of dimension 2 because you have two vectors in basis. So you'll have two columns here and two columns on the other side. These two columns are linearly independent. So that means that you'll have two linearly independent rows also. So that means that you'll have a bunch of zeros below. So you have identity 2 by 2 in the corner and then zeros below. And this part here is your transition matrix, the part in red. Because the solution is AB, and CD. So you just find them A, B, C, D. So the transition matrix is actually found as coefficients A, B, and C, D in column. When it's easy, you can instead compute the transition matrix from C to B by computing the inverse. So let's see now an example where we have actually some vectors that we don't even know what they are, but we are given coordinates of vector Z in basis B, and coordinates are 5 and -4. So the question is, you need to find me the coordinates of Z in basis C. Well, that's not complicated, because we are given coordinates in basis B. We already computed the transition matrix from basis B to basis C. That shouldn't be a problem now. So coordinates of Z in basis C are equal to, so that's how you get it, transition matrix from basis B to basis C times coordinates of the vector in basis B. So when you do the product, the result is coordinates in basis C. So you just do the product of transition matrix from B to C and coordinates in B, you'll get coordinates in C. Ta-da! Straightforward. Second problem, find the vector. I know the coordinates of the vector in a basis B. Now I know the coordinates of the same vector in basis C, but what's the vector? I don't know who's the vector. I need to find him. Well, that's not a problem, because by definition of the coordinates of Z in basis B are 5 and -4. What does it mean? It means that Z is 5 times the first basis vector in basis B plus -4 times the second basis vector from basis B. Do the computation and you get the vector Z. You could use the coordinates from basis C and basis C also, so that's another option. You don't need to, but you just need one of them. So let's say you use the coordinates from basis C, 5 and -9/2. Well, that means that Z is 5 times first vector from basis C plus -9/2 times the second vector of basis C. Compute, you'll get the same vector, obviously. You must get the same vector, because vector Z has different coordinates in different bases, but it's the same vector. Similarly here, I'm given vector P, which I don't know what's the vector, but I know that the coordinates of P in basis C are 3 and -2. So I have the coordinates of P in basis C. Question, what are the coordinates of P in basis B? Not complicated again. Coordinates of P in basis B are given by the product of transition matrix from basis C to basis B times coordinates of P in basis C. Do the product and you'll get the coordinates of vector P in basis B. So this is the transition matrix from C to B. Times the coordinates in C. Do the product, you get coordinates in B. Finished. Second question, what's the vector P? I have his coordinates, but I don't know who's the guy. Well, no problem. Since I have the coordinates in basis C, it's 3 and -2. That means that P is actually equal to 3 times first vector from basis C plus -2 times the second vector from basis C. Compute. This is my vector P. Another way to compute it, we don't need it, but you could, if you wish. You could use the coordinates of P in basis B that we just computed in this part here. So coordinates of P in basis B are 3 and -1. What does it mean? P is equal to 3 times first vector from basis B plus -1 times the second vector from basis B. Then you get the same vector at the end. Obviously the vector is the same in both cases. We have the coordinates, we just use the definition of coordinates to find the vector itself. So these are the things that are normally not complicated. The only thing that takes a little bit of time is computation of transition matrix. But again, the process is not too complicated. Be careful about the number of vectors in the basis. So if you have a linear space, like in this case linear space W of dimension 2, that means you have 2 vectors in a basis. Your transition matrix from one basis of W to another basis of W will be 2 by 2. And that matrix is square, obviously, and invertible, obviously. If your linear space has dimension 3, for instance, doesn't mean that is R3 necessarily. It could be some subspace of R7, so you have vectors with 7 components. What will happen if you have, let's say, some subspace of R7 of dimension 3, so subspaces of dimension 3 is generated by 3 linear independent vectors from R7. So dimension is 3, each basis has 3 linear independent vectors, but each vector has 7 components. That's fine, no problem at all. Now a transition matrix, in this case, from one basis to another, will be 3 by 3. And that matrix will be obviously square and invertible. So that's all you need to think about.
Here are some exercises for you to practice in both books. The exercises with the star require a little bit of thinking, the definitions, but other exercises are purely computational, so you need to know how to compute the coordinates of a given vector in certain basis, and also how to find or build or compute the transition matrix from one basis to another. Some extra problems here, if you wish to practice more. You have 3 ordered bases in R2, and you need to build the transition matrices. All of these transition matrices will be 2 by 2 invertible, so you can take advantage of that. And here are given some coordinates of some vector in one basis, and then you need to find the coordinates in the other 2. This problem is solved just to point the importance of the word ordered basis. So I have basis of R2 1001 and 0110. So all I did is just change the order of the basis vectors, but that will change the order of coordinates, obviously. So you can compute the transition matrix in both cases. So transition matrix from B2 to B1 means that I need to find coordinates of each vector from B2 as linear combination of vectors in B1. So I need to find the coordinates of vectors from B2 in B1. So just simply solve. Here we have already the correct form identity slash something, and that something is automatically the transition matrix. Obviously it's 2 by 2 and it is invertible. And the transition matrix from B1 to B2, similarly B2 slash B1, you need to solve. Here is just swap the 2 rows, it's very simple, and then you get your transition matrix. Now if I'm given coordinates of a vector G in basis B1, 5, 2, what are the coordinates of the same vector G in basis B2? Well, I multiply the transition matrix from B1 to B2 by the coordinates of the vector in B1, so do the product matrix vector, and I get the coordinates of the vector G in basis B2. Obviously, we just changed the order of coordinates because we changed the order of bases. And the vector obviously is 5, 2. So those are the things that you need to focus on: how to build a transition matrix, how to find coordinates of a vector in a given basis, and also given coordinates of a vector in one basis, how you find the coordinates of the same vector in another basis using the transition matrix. So these things are pretty straightforward, but require some practice to make sure you know the concepts and you know how to actually do the work.